Section 4.9, antiderivatives. All right, so we've been spending a lot of time talking about the derivatives of a function, where we spent most of chapter 3 looking at how to differentiate different types of functions. And then chapter 4, we kind of put the derivative to use for us. Well, in this section, we're going to introduce basically the reverse process, right? So if I know what the derivative of a function is, can I find the function, right, which we're going to call the antiderivative. Now, just like with differentiation, there are processes involved in finding antiderivatives. Some processes are a little more straightforward, like power rule. Just like with differentiation, use of the power rule is a pretty straightforward process for finding an antiderivative. There's a power rule that, again, is a pretty straightforward process. There are other types of functions that we kind of have to know from memory what the antiderivative would be. Say, for example, trig functions, right? Because there is really no process for differentiating a trig function. It's just I know what the derivative is. And so the same thing is true for an antiderivative. But then after that, the processes for finding the antiderivative of a function get a little more complex, right? Definitely compared to differentiation. The rules and processes that we have for differentiation tend to be pretty straightforward. You recognize the type of function you have, you follow the process or product or quotient rule, that type of stuff. But for finding an antiderivative, that can be a bit more complicated. So we're going to look at the power rule in this first section, 4.9, and a couple of other types of functions that are pretty straightforward. So this section is going to be, I think, a fairly straightforward section. But then when we get into chapter 5, we're going to have to get into a little more complex situations. And finding antiderivatives and a little bit more about what the antiderivative represents. Because we've talked about with the derivative, what does the derivative represent ultimately? It's the slope of the tan line or the slope of the curve, right, at along for a given value of the function. Excuse me. Well, then what does the antiderivative represent? Right? So what if I take the antiderivative of a function? What does its antiderivative represent? It has a meaning. It actually calculates something. So we'll talk about that in chapter 5, along with introducing processes for finding the antiderivative of a little more complex functions. Now, we're only going to do a certain amount in chapter 5, and then in chapter 6, we'll do a little bit of application with the antiderivative. But then that's where we're going to end it. Those of you that are heading on into Calc 2, the first part of Calc 2 is finding antiderivatives, or what is called integration, but in much more complex situations, right? So just kind of keep in mind, ultimately what I want you to keep in mind here is that we are only scratching the surface of processes that we use to find the antiderivative of a function. It's a lot more complex, or can be a lot more complex, and that is something that would be addressed going forward in Calc 2, okay? So just keep that in mind. But 4.9, like I said, that tends to go pretty well because, again, all you're dealing with here is power rule. All right, so in general, if we know the derivative function, call it little f, then we can find the original function, which we're going to call cap f. Now, be careful with notation here. There's different notations that are used. I don't want that to trip you up as well. So notice in this case, we're calling the derivative little f, whose antiderivative, the original function, is cap f. We could also say that our derivative is f prime, right, whose antiderivative is just f. So it just depends on the notation that's used, right? So don't let that be a stumbling block or be a hurdle for us. I always say you just got to watch the notation. Depends on what you call it. So definition, we'll say that a function cap f is called an antiderivative of our function little f on an interval I if cap f prime is equal to little f for all x in that interval. And don't worry too much about the whole interval thing just yet. We'll talk about that more later. So in other words, cap f is the antiderivative of little f if the derivative of cap f, f prime, is little f. Okay. Now, there is one major little issue to keep in mind here. Let's say, for example, that I've got our function little f as 3x squared. And I want to find cap f. I want to know what is its antiderivative, right? So your question then is, what is 3x squared the derivative of? And if you look at cap f equal to x cubed, right, then cap f prime would be 3x squared, right? So 3x squared is the derivative of x cubed, which means x cubed is the antiderivative of 3x squared. But it's not the only one. If you look at x cubed plus 10, let's let cap f equal x cubed plus 10, whose derivative, again, notice, is still just 3x squared, because the derivative of the 10, the derivative of the constant, is 0. So then the antiderivative of 3x squared is still x cubed, but in this case it's x cubed plus 10. Or what if we let cap f be x cubed minus 4, whose derivative, f prime, is still 3x squared, whose antiderivative would be, again, x cubed, but in this case minus 4. So the question is, well, which one are you dealing with? Well, it could be any one. So in other words, if I look at these three functions, they all have the same derivative, right? But the antiderivative could be different. We know one part of the antiderivative, it has to be x cubed, but then it's always, notice, x cubed plus or minus a constant. So when we find the antiderivative of a function, this is something to keep in mind. We're going to start by finding what we call the general antiderivative of a function. So they're actually, for a given function, there is an infinite number of general antiderivatives for that function, because I can find the most basic antiderivative, but I have to tack on a constant, because I can have any constant tacked onto that function x cubed, and I get the same derivative of 3x squared. So that's one thing to keep in mind. Now, if I am given certain conditions, if I'm given information specifically about the derivative or about the antiderivative, then we may be able to find a specific antiderivative. Okay, so we'll get to that here in a little bit. So we'll start here, though, first with what we call the general antiderivative. So theorem, if f is an antiderivative, if cap f is an antiderivative of little f on an interval I, then the most general antiderivative of little f on I is that function cap f of x plus c, where c is representing some arbitrary constant. So anytime you find an antiderivative, unless you're given specific information that allows you to find a specific antiderivative, you're always tacking on the plus c. So we want to make that a habit. And it's not a minor thing. I mean, you think about it, like we said, there's an infinite number of antiderivatives for any given function. And if you leave off that plus c, then you're only giving me one antiderivative of an infinite number. Right? So you've actually left most of them out. So it's not a minor detail, it's a major deal. So first, the power rule. Now I'm going to do the power rule, and then I'm going to come back to that little recall statement. So the power rule, remember our power rule for finding a derivative. Right? If we have a power function, what do? We multiply by the exponent and then decrease the exponent by 1. So to find the antiderivative, we're just going to reverse that process. So if I have a function little f of x of the form x to the nth power, then to find the antiderivative, we're going to increase the exponent by 1 and divide by the new exponent. Right? So for differentiating, we multiply and decrease. For the antiderivative, we increase and divide. Right? So we follow a reverse process in the reverse order. So obviously, be careful in a given situation. Am I finding the derivative? Because we're not done with derivatives. We're still going to differentiate functions. So am I finding the derivative of a function, or am I finding its antiderivative? So be careful which direction you're going. So to find the antiderivative of a power function, in this case I'll call it cap f, the antiderivative of little f, we increase the exponent by 1, we divide by the new exponent, plus c. All right, always plus c, always plus c, always plus c on an antiderivative, unless we have specific information. Now, this power rule holds true provided that n is not equal to -1, because notice, if n was -1, if I have x to the -1 power, and you follow the power rule, it says increase the exponent by 1, well, -1 plus 1 is 0. And then I would have to divide by the new exponent. So that gives me x to the 0 over 0, which is undefined. So the power rule works provided that our exponent is not -1. But notice, this goes back to something we should recognize, that if x is -1, I could write our function little f as 1 over x, right? That's x to the -1. What's the antiderivative of 1 over x? Okay. Now, we had a little discussion about this earlier, previous section. This is one of those things I tell you to kind of tuck away and remember we'll bring it back up later. This is that time. We know that the derivative of ln of x is 1 over x, right? Because we did a bunch of differentiation with that type of function. But we also at some point showed that the derivative of natural log of the absolute value of x is also 1 over x, regardless of the value of x, right? And then x could be positive, x could be negative in this case. So when we talk about the antiderivative, or the general antiderivative of 1 over x, it's not just natural log of x, it's natural log of absolute value of x, plus c. And if you leave off that absolute value, then again, you've left off half of your antiderivative. So again, it's not a minor deal. Even though, well, we don't deal with natural log of absolute value of x very often. We normally just deal with ln of x, the basic function. But in its most general context, the antiderivative of 1 over x is natural log of the absolute value of x plus c. Okay? So again, don't forget that. Again, it's not a minor deal. You're leaving off half of the antiderivatives if you leave off the absolute value. All right. But other than that, I mean, power rule is pretty straightforward. I mean, just like differentiating with power rule, it's pretty straightforward once you get the hang of it. Just again, be careful. Make sure you're not going the wrong direction, and then don't forget to tack on your arbitrary constant, your plus c, when you're finding your general antiderivatives. So for example, like I said, this is about as straightforward as it gets. If I have a function little f equal to 3x to the 4th, so again, power rule for a power function for antiderivatives says, and again, I'm calling this cap f because our function is little f, so its antiderivative will be labeled as cap f. So we say we increase the exponent, so I've got 3x to the 5th divided by the new exponent plus c. And you're going to leave that plus c off a lot of times. It's going to happen. I still do it sometimes, but you just make sure you go back and catch it before you're done. Okay. So at some point, at least at the end, once you're done with whatever your anti-differentiation process is, in giving your final general antiderivative, make sure you tack on that arbitrary constant. Otherwise, it's incorrect. So I just rewrote that as 3/5 x to the 5th plus c. Number 2, or part B. I have little f of x equals 4. Remember, when you differentiate 4x, you get 4. So the antiderivative of 4, and if you follow power rule, I mean, it's still 4x to the 1st over 1 plus c, or just 4x plus c. So again, that's something you can kind of commit to memory. The antiderivative of our constant is just the constant times x, or whatever your variable happens to be. And also keep that in mind too. I mean, anytime you find an antiderivative, you can always check it. Because once you find the antiderivative, if you differentiate this function, then you should end up back with the original function, right? Because the derivative of 4x is 4, and the derivative of the constant is 0. All right, so I mean, you can always check an antiderivative by differentiating to make sure you get back the original function. So to that extent, it's kind of like no excuse, right, for having an incorrect antiderivative, because you can always differentiate to double check. So part C, that just throws in multiple terms, so nothing different there. Just like with differentiating multiple term power functions, you can find the antiderivative term by term. Right? So for f of x equal to 2 plus x squared minus 6x to the 5th, I've got cap f of x, the antiderivative, as 2x plus x cubed over 3, increase the exponent, divide by the new exponent, minus 6x to the 6th over 6 plus c. I notice, like I said, you're going to leave it off a lot of times. Just make sure I tack it on at the end. And then I just simplified. Of course, we always want to simplify when we're done, just like when we're differentiating. So I've got 2x plus 1/3 x cubed minus x to the 6th, in this case, plus c. Now, I told you already earlier that there are some functions whose antiderivatives we just know. I mentioned the trig functions. Another one is your exponential function base e. Right? Because remember, the derivative of e to the x is e to the x. So not only is it its own derivative, it is its own antiderivative, right? So if the derivative of e to the x is e to the x, then the antiderivative of e to the x is also e to the x. So for f of x equals e to the x, cap f of x, the antiderivative, would also just be e to the x plus c, plus our arbitrary constant, all right? So again, that just continues to make e to the x a nice function to work with, differentiation or antiderivative. Now for the trig functions, right, this is going to be memorization just like the derivatives, but there is one thing to be careful of here, and that's going to be the SIGNs, the signs of the function, whether it's positive or negative, because remember, the derivative of sine is negative cosine. The derivative of cosine is negative sine. So if I'm looking for the antiderivative of sine, I know that the antiderivative of sine has to be a version of cosine, because the derivative of cosine is negative sine. So when I find the antiderivative, I have to take that negative into consideration, and the antiderivative of sine would be negative cosine plus c. Now again, you can double check that, because again, this derivative of cosine is negative sine, but our function is positive. So I need that extra negative in front of that to make that derivative positive. So again, like I said earlier, you can double check your antiderivative by finding the derivative, and especially in the case of these trig functions, just to double check your SIGNs. All right. So you've got to watch, because with sine and cosine, yes, they are derivatives, antiderivatives of each other, but there's a positive or negative thing there that you have to be careful of. So be careful with that. Double check it, and you can do that by differentiating, and if you need to tack on the extra negative, then you do so. All right, C. I've just got, again, multiple terms in this thing. I've got f of x, little f equals 3e to the x plus 7 secant squared. Right? And so again, the antiderivative of e to the x is e to the x. The constant doesn't change that. The antiderivative of 3e to the x is still just 3e to the x. Plus, again, the constant doesn't change anything. But just like differentiation, the constant times a function, its derivative is the constant times the derivative. Same thing is true for antiderivatives. So here I have to recognize that, the question is, what is the antiderivative of secant squared? So with your trig functions, you have to recognize what secant squared is the derivative of. And secant squared is the derivative of tangent, so the antiderivative of secant squared is tangent. So our cap f antiderivative is 3e to the x plus 7 tangent of x, plus our arbitrary constant plus c. Okay, so yeah, exponential function base e, pretty straightforward there, but the trig functions, we have to memorize them both ways, plus you have to watch the positive or negative, right, sign of it. And then D, I just went ahead and threw one in with some radicals. Again, those are power functions, right? We've done plenty of power rule with that type of function. So nothing changes here. We just have to watch, again, the direction that you're going with the exponent. So I've got the 4th root of x cubed plus the cube root of x to the 4th as our function. And just like when I was finding derivatives, I went ahead and rewrote it in as rational exponents. So x to the 3/4 plus x to the 4/3. And then we find our derivative using the power rule. So I'm going to multiply. See, there I go going the wrong way. I'm going to increase the exponent by 1. So I have to add 1 to 3/4, giving us 7/4. And then we divide by the new exponent. Another way you can think of this, if you want to shortcut this, since my exponent is a fraction, and I divide by the fraction, I could then multiply by the reciprocal. So back here, I just rewrote that as 4/7 times x to the 7/4. So if you want to shortcut that, You can increase the exponent by 1 and divide by the exponent. But in the case of a fraction, dividing by the fraction means I'm going to multiply by the reciprocal. So you can take a step, and if you want to bypass this step and go straight to this step, that's fine. Okay. So then the next one, right, was x to the 4/3. So I have to increase the exponent. So I'm adding 3/3. Right? So I get x to the 7/3 divided by 7/3, or multiply by the reciprocal. I've got 3/7 x to the 7/3 plus our arbitrary constant plus c. Yeah, so same thing is true here, when we did differentiation. You've got to do your fraction calculation, but like I keep saying, just watch your direction that you're going. Are you differentiating? Or are you finding the antiderivative? Do I need to decrease or increase the exponent? That catches us, and sometimes it's not intentional, right? So just be careful which way you're going with your process. All right, but that's basically it. I mean, that's basically power rule. So what about the next one? Here I'm given f double prime. All right, so notice my notation here. In the previous examples, we were given the function and looking for the antiderivative. So basically, we were given f prime and we were looking for f. Here I'm given f double prime and I'm asked to find f. It doesn't change anything. It just means I'm going to have to find the antiderivative twice, right? So if I start with f double prime, 2 plus x cubed plus x to the 6th, I can find its antiderivative. The antiderivative of f double prime would be f prime. And again, this is a straightforward power rule. So 2x, x to the 4th over 4, x to the 7th over 7, plus our arbitrary constant, right? Because we're finding the antiderivative. Then I can find the antiderivative of f prime, which would now be our function to the left. So again, I'm just following power rules. So the antiderivative of 2x would be 2x squared over 2. Antiderivative of x to the 4th over 4 would be x to the 5th divided by 5 times that 4 that's already there. So again, I'm just increasing the exponent by 1 and dividing by the new exponent. Likewise, I've got x to the 8th and then dividing by 8 times the 7 that's already there. But then watch the constant, right? What's the antiderivative of c? Remember, c is a constant whose antiderivative would be c times x. Right? Just like we had earlier, I think the antiderivative of 4 is 4x. So the antiderivative of c is cx. Plus, we need our arbitrary constant. I just tack on another arbitrary constant. I called it d. I don't want to call it c again because that implies that they're the same, c and c. Unless you do something like, call this one c sub 1 and call this one c sub 2. You'll see it done that way as well. But I like using different letters, but you could also do it that way using subscripts. The main thing you don't want to do is call them both c, because that kind of implies that it's the same constant. And maybe it is, maybe it isn't. Okay? So, but regardless, right? So the first iteration I went through, found the antiderivative. We tacked on a plus c. When I find the antiderivative of that, it's cx, but then I need to tack on another arbitrary constant. And then I just simplified it from there, right? So here's our function f of x. Let me label it as such. X squared plus x to the 5th over 20 plus x to the 8th over 56 plus cx plus d. So we started there with the second derivative and we found our function. All right. Just as to mention this for future reference, if you're heading into higher levels of math, so if you're like going into engineering or a math major or something like that, computer science maybe, eventually you're going to take a course titled Differential Equations. And differential equations involve equations involving derivatives of functions, right? So they're called differential equations. Excuse me. That's something that you will cover later, again, depending on if you're heading into those higher levels of mathematics. So differential equations. It's a pretty useful topic, actually. But it involves use of derivatives. Anyway, so continuing. Thus far, all right, so we found just those general antiderivatives. Okay? Now, what I mentioned to you earlier was that if we are given information, if we are given certain conditions with respect to our function, then we may be able to find a specific antiderivative. Okay? So in other words, I should be able to give you enough information to where I can find the C value and I can determine what that arbitrary constant is. It's a specific value for a given situation. And then we can give you the specific antiderivative. Okay? So for example, for the next one, I have f of x equals e to the x plus 200 times 1 plus x squared to the negative 1. Now I threw this one in just to remind you of a type of function that we've seen before, because I don't want you to forget about your inverse trig functions, because I mentioned at the time they kind of throw these in every now and then, so we need to recognize them when we see them. So I have this function f of x e to the x plus 200x times 1 plus x squared to the negative 1, or I could rewrite that 200, how about 20, e to the x plus 20 over 1 plus x squared. We're also told, though, that cap f of 0 equals negative 2, right? So in other words, notice I'm given information about the antiderivative. So that's what I was saying about given certain conditions. Find our antiderivative f of x, and in this case, since I know something specific about cap f, we should be able to find the specific antiderivative. So first thing we do is we go through our general antiderivative process, same as before. Now what I want you to recognize, remember that the derivative of inverse tangent of x is 1 over 1 plus x squared. So again, I'm reminding you of that because you're going to see that one pop up a couple times in homework problems going forward. So recognize that the antiderivative, so first of all, our antiderivative of e to the x is nicely, again, e to the x. So here's our cap f, our antiderivative. And then the antiderivative of 20 over 1 plus x squared, or if you want, you could write that as, if you prefer to see it this way, 20, try that again, 20 times 1 over 1 plus x squared, if it's easier to see it or recognize it that way. But main thing, when you see that 1 plus x squared in the denominator, start thinking inverse tangent. All right, so antiderivative of e to the x is e to the x. Antiderivative then of 20 over 1 plus x squared, or 20 times 1 over 1 plus x squared. The antiderivative of 1 over 1 plus x squared is inverse tangent, so I get 20 times inverse tangent of x plus our arbitrary constant, plus c. All right, so that's our general antiderivative. Then we can make use of the information that's given. We are told that f prime, or that cap f of 0 is negative 2. So I have a function, cap f of x. We know one of its function values. So f of 0, we'll plug 0 into f, e to the x plus, or e to the 0 rather, plus 20 times inverse tangent of 0 plus c. And we know that that is equal to negative 2. Right, so once you find your general antiderivative, you plug in your given x value, set it equal to the given function value. And now I have the only unknown there as c, so I can solve that equation for c. So e to the 0, any non-zero number to the 0 power is 1. Inverse tangent of 0 turns out to be 0. You can always plug that into your calculator if you don't recognize or know that. Plus c equals negative 2, and so I'm just solving that for c. So I've got 20 times 0 is 0, so c then would be negative 2 minus 1, or negative 3. Right? So once you plug in the information that's given, the value for x and the value for the function, solve the equation for c. Now, once you have your c value, don't forget to go back and plug that into your general antiderivative to give the specific antiderivative. So all I'm doing then is I'm just replacing the plus c, let me not circle that one, this one, with the c value that we just found. Right? So here's our specific antiderivative. Cap f of x then would be e to the x plus 200 inverse tangent of x minus 3. Right? So that's how that works. Okay, and again, that tends to go pretty straightforward. Just gotta, remember what it is that you're doing there. once I'm given the specific value. So here's another example. I have a couple of these. So for the next one, here I'm using f and f prime. So f prime of x, our derivative, is 2x minus 3 over x to the fourth, provided x is positive. So notice that kind of eliminates the undefined issue. We want our function to be continuous and over our interval. So 2x minus 3 over x to the fourth, and we're also given that f of 1, little f of 1, which is our antiderivative in this case, is 3. And then we're asked to find f of x. Now again, I just use the different notation here because I can tell you it just depends on which way you want to label it. So here's our original function, and since we're finding its antiderivative, I'm calling it f prime, whose antiderivative then would be f, okay? Instead of using the little f and cap f that we used before. All right, but I am going to find the antiderivative of that function, so I went ahead and put it in the form to use the power rule. So I've got 2x minus 3x to the negative 4. Antiderivative, f of x, 2x squared over 2. 3x, now remember I'm increasing the exponent by 1. Be careful with those negative exponents. I'm increasing by 1, so negative 4 plus 1 is negative 3, and then I divide by the new exponent. Plus our arbitrary constant, plus c. So there's our general antiderivative simplified. I've got x squared plus, because I've got two negatives over here, so plus 1 over x cubed plus c. That's our general antiderivative. And then we are given a specific condition that f of 1 equals 3. So I'll take f of 1, plug 1 into that function, so it's 1 cubed plus 1 over 1 cubed plus c. Or 1 squared rather, plus 1 over 1 cubed plus c. And I know that's equal to 3. And then we'll just solve that for c. So that'd be 1 plus 1, or 2, plus c equals 3. Subtract 2, and I've got c equals 1. I trust you can solve that for c. And then once we find our c value, our arbitrary constant, then we'll go back and plug that into our general antiderivative. So f of x is x squared plus 1 over x cubed plus 1. And I also went ahead and included the fact that, as we said at the beginning, x is positive, x is greater than 0. If you leave that off, I'm not going to make that a big deal. But that is a limitation on the function. Right? Remember the domain of the function, domain of the antiderivative, or the domain of the derivative, I should say. And the last one is another one with a second derivative, or starting with the second derivative. But again, it's not going to change anything. We just have to do it multiple times, right, in terms of finding our antiderivative. So this time, though, if I'm looking for a specific antiderivative, we're starting with g double prime, and we're looking eventually for g. We notice we're given information not only about the antiderivative of g double prime, which is g prime, we're also then given information about the function g. All right, so in other words, I have to be given a specific condition at each step along the way if I'm going to eventually find the specific function. But otherwise, we're going to follow basically the same process. If g double prime is 4 minus 6x minus 40x cubed, then I start by finding the antiderivative of g double prime, which is g prime. And that's, again, straight power function, so 4x, 6x squared over 2, minus 40x to the fourth over 4, plus our arbitrary constant c, and then I just simplified it, so I got 4x minus 3x squared minus 10x to the fourth plus c. That's g prime. And then we are given a specific condition, specific information about g prime. So I can use that to find c. So g prime of 0, plug 0 into g prime. So 4 times 0 minus 3 times 0 squared minus 10 times 0 to the fourth plus c equals 1. Well, that's all going to be, those are all going to be 0, so I've got c equals 1. So that gives us g prime, the specific g prime, plugging 1 in place of c, 4x minus 3x squared minus 10x to the fourth plus 1. And then we'll repeat the process and find our antiderivative of g prime, which is g, power rule, 4x squared over 2 minus 3x cubed over 3 minus 10x to the fifth over 5. The antiderivative of 1 would be x, plus I need an arbitrary constant. Now you can call that c again if you want, because there's only one arbitrary constant there. I just went ahead and used d. Or again, you could use c1, c sub 2, and so forth. So again, I just simplified it. I've got 2x squared minus x cubed minus 2x to the fifth plus x plus d as the general formula for our function g. And then we are given specific information about g. We are told that g of 0 is equal to 2. So as before, I'll go ahead and plug that in. G of 0, which is the function we just found. So 2 times 0 minus 0 minus 0 plus d equals 2. Right, that's the function value. And again, that's just going to give me d equals 2. I mean, polynomials are always nicer to work with. And then once I have my d value, again, I'll plug that into our function g, the general that we just had. So then we have our function g of x, 2x squared minus x cubed minus 2x to the fifth plus x, and then subbing in place of d, 2. Right. So again, I mean, that tends to go pretty well, and especially with the polynomials, you know, the power rule. All right, but just a couple of little things I mentioned to you along the way. Again, general antiderivative, don't forget your plus c. That's a deduction. And then again, in these cases where you're given specific information, you can find the value of the arbitrary constant to give the specific antiderivative. And then again, the other thing, I guess, is just the notation. Watch the labeling depending upon whether you're using little f and cap f, or if you're using f prime and f. Otherwise, that's it for that section. Read section 5.1. I'm not going to do a lecture on that section. I'll do a summary in the section when I do the lecture on 5.2. Okay, but section 5.1 introduces a lot of notation and terminology going forward involving this idea of finding an antiderivative, which ultimately is what we call the process of integration and finding an integral. All right. So 5.1 lays kind of a lot of the little groundwork for this. I'll summarize that. It's going to have some notation in there that you need to be familiar with. So read through that section before you look at the lecture for section 5.2. All right, that's it for this section.